Thank you very much, Brian, for inviting us to give this talk, and appreciate your kind introduction. So today we're going to talk about RMS-Equivalent EMT Inverter model, as well as the integrated GFM, grid forming, GFL, grid following controls for autonomous operation of inverter-based resources. This is the outline of our talk. We're going to give a summary information about the experimental platforms that we're using. And then we're going to switch gear to talk about the modeling and the control framework for these inverters. And then we're going to break it down to two parts in terms of the technical discussions. The first part deals with Hammerstein-Wiener PV modeling, and then second part addresses integrative GFM and GFL design. And then we'll present several case studies and ongoing work that we are engaged in terms of integration of the aforementioned modeling and the control techniques. What's shown here is the test setup at UCF for the 5 kW Great Link software-defined inverter platform. The Great Link inverter is a 3-phase, 3-level active neutral point clamped converter. And it's called software-defined by the nature that it is Simulink compatible. So we can do high-level programming and develop control and modeling architectures and download to the software. I apologize for the rain here. So the reason we choose this platform is that we believe the software-defined network will provide the flexibility of implementing a variety of controls and demonstrate their effectiveness. And this is just one of many of the inverters we have will be using in the modeling and the control. The second platform, which we're talking in a minute, is the TAPA's, also software-defined inverter. Just to give a little bit more insight about the Great Link inverter, it has 6 transistor switches per phase, and 4 for the inner loop switching at 48 kilohertz, and then 2 out loop transistors switching at 60 hertz. And that's the bulk of the switching circuit in the middle. And for the PV inverters, of course, it has the MPPT, the DC boost converter at front, and then followed on the output side, the standard LC or LCL AC filter. And that's the basic configuration that we'll be using in terms of designing control and develop dynamic models. We're also using this 4DG microgrid, which is developed based upon CERT's microgrid that was proposed by Oak Ridge National Lab. And we have a benchtop testbed using the TAPA's software-defined inverters. So the overall modeling and the control framework is shown here on this particular slide. At the bottom of the slide, you will see a distributed secondary control that manages multiple DGs. And the secondary control will be taken as granted in terms of this particular talk. So we can focus upon the primary control design, as well as the modeling, the dynamic modeling of the inverters, as well as associated PV panels and MPPT controls. Depending upon the signals that can be measured, in real application setting, we can either develop one or two Hammerstein-Wiener model for the PV as well as the inverter stage. What's shown on the graph here is that we have, if we would have a measurement of DC voltage and DC current, then we can develop a HW model for the PV panel, the DC boost converter, as well as the MPPT controllers that are involved. And then we can develop the second HW model for the switching circuits that corresponding to a particular platform of inverter. The inverter model, there are two options. One is to use the average model, which we'll get into some of the details later. And obviously, the average model does not provide the electromagnetic transient responses of the switching model. So the goal here is twofold. One is, develop the modeling techniques that allow us to better describe the dynamics associated with the switching model, and then also for us to compare its performance with the average model and the subsequent analytical design of the primary control of the inverters. And then that will give us the opportunity to provide advanced control so that we can compensate for the electromagnetic transients. The rest of the network is pretty standard. Of course, we use coordinate transformations and that give us a DQ0 components. That's where the domain we're going to use to do the analysis and design, and the filters are parameterized in standard configurations. We're going to address both the grade forming GFM inverter design, control design, as well as the grade following control design. And the goal there is to integrate so that the inverters can switch between the two modes autonomously. I'm going to turn the floor to my colleague, Tom, who will provide the details about the HW modeling. Tom?
Okay, thank you. Thank you, Zhihua. So the Hammerstein-Wiener, if you haven't seen that structure before in the green box, there are two static nonlinearities, F1 and F2, multiple input and multiple output. And we implemented those in neural networks with a 10H activation function. And then in between, there's a linear dynamic function we label H1, also multiple input output, and that's fit in the Z domain. And so we trained that model with a set of transient simulations, and it could be either from a laboratory test or EMT simulations, whether it's ATP or PSCAD or MATLAB. We sought the HWPV model to generalize to different kinds of inverters. We're considering several in this project, and a lot of times we'll have a very detailed model of an inverter, but that isn't always practically the case. There may be proprietary details that are hidden or not known. The other thing I'll point out, and when we train the model, the inputs, weather and control inputs are in blue there. The outputs we're interested in are in red, the D and Q axis currents and the DC voltage and current. The grid side is in magenta, and so what we will do is create grid transients by switching load components on or off. And what that does is change the ratio of VRIRMS and IRMS. So in other words, the impedance seen at the terminals of the inverter looking out. What we want to do is present a Norton equivalent control current source injected into the grid. And so the training inputs, if you look at the inputs to F1, we're feeding back VRMS. And we also use a polynomial input feature, the irradiance G times VRMS, and that's kind of a proxy for the loading effect. So we wanted to incorporate loading impacts on the PV stage, the DC stage, and also in the inverter itself. So that's the overall framework, and what we can do is swap in or out different types of nonlinearity models for the PV panels, and the MPPT control has a large impact. And the links and references are shown there. Next slide, please. Okay, might ask why do we need an HWPV model for the inverters, especially if we have a detailed EMT model like is often the case in research. So it runs a lot faster. The HWPV can be portable among different simulation tools. If you have an EMT model for one tool, it doesn't run easily in something else. You can get an HWPV model parameterized without proprietary data, so a vendor could do this ultimately with type tests. We're getting ready to do some testing in UCF's lab now, especially for single-phase inverters where you usually can't get an EMT model. We were delayed by some of the supply chain issues during COVID, but we're just ready, in a few weeks to start testing single-phase inverters, collecting transient voltage and current data the same as we would in a transient simulation, and generating hundreds or thousands of training cases to train this block diagram model. It is generic, but we can add functions, for protection functions. It's suitable, we think, for DER aggregation studies and other studies where the actual model of the inverter isn't known yet, but you need to do more detail than just a simple average model study. Next slide, please. Okay, so this is an example training set from the Alternative Transients Program, which is free to use, ATP. This is a three-phase inverter with an average model. We've run different cases with a switching inverter model, an average model, different kinds of DC. Sometimes they have a boost stage in the DC, sometimes they don't. Sometimes it's transformerless, sometimes it has a transformer. But we're trying to, in the test sequence, start up the inverter, ramp up the irradiance, and then at 3 seconds in, we'll initiate some kind of disturbance in the control variables, the D and Q axis modulation index, for example, or a grid transient which affects the VRMS, and that becomes a training input. Next slide. Okay, so these are the training case outputs that we're trying to fit. So there's 1,500 of them there, and you can see they all behave pretty well. They ramp up to some steady value, and then when the transient occurs, they ramp with different time constants or ramp times to a different value. And the outputs we're trying to fit are the DC voltage and the DC current, and then ID and IQ for the balance case. So those are steady quantities there. Next slide, please. Okay, so these are some of the training error results that we get for a one-phase switching model, a three-phase balanced, three-phase unbalanced, three-phase combined, balanced and unbalanced, and then a Simulink model that was run at UCF, not at PNL. So UCF just sent us the transient data, and we fit the HWPV model to that. Look down about 6 or 7 rows into the table, and you see the EMT simulation times up to 30 hours. For the Simulink model. So this is one of the benefits of the HWPV, that it can run in seconds. We need a lot of training cases, lots of iterations to train the model. The training time is usually less than the EMT simulation time, but it's not insignificant. We're also doing training in the Z domain, so we will discretize at 1 or 2 millisecond time steps. So we're trying to catch the fast dynamics. So we're not capturing the switching transients only in their impact on the RMS type dynamic model. This is a sample on the left of the training result for one of the UCF cases, and so it is pretty good. Our criteria for per unit RMS error was 0.05 or 5%. So these are all well below that, and visually they look pretty good. So the training process can work pretty well. Before we go off of this slide. Looking at the second and third columns of data there, we got pretty good results with a three-phase balanced model, and also pretty good results with a three-phase unbalanced model. But when we tried to combine them, it's taken more iterations in training time, and still the RMS error, particularly in VDC, isn't good enough. So we're rethinking a little bit, and maybe we need to have separate models, separate modes of operation for the balanced and the unbalanced. More about that later. Next slide, please. Okay, so this is want to step back a little bit and talk about that unbalanced modeling option. So the AC side is a little bit more complicated. When you have an unbalanced, and for now we're just thinking of single phase load disturbances, you're going to get oscillatory behavior in ID and IQ. And you also get some non-zero I0. And those quantities can oscillate at either 60 hertz or 120 hertz if the control frequency is 60 hertz. So what we did is augment the training. We're getting separate VD and VQ outputs to feed back into the model. And we're going to inject current sources that are going to include low pass and high pass quantities for ID and IQ, and maybe even I0. So the basic framework is pretty much the same. If you were following along the outputs of F2, there are more of them. Instead of just ID and IQ, we have 6 zero sequence, high pass and low pass quantities. So what do those mean? Next slide, please. Okay, when we do training sets, generate the training sets for the imbalanced disturbances, we will ramp up to an initial condition. And here, this is a later training set. So notice we don't just start with values of 1 for MD and 0 for MQ, but we're capturing a range of like 0.84 to 1.16 per unit for the MD, and then plus or minus 0.2 per unit for the MQ. And we'll make a change in MD and MQ, and we'll also initiate some single phase load changes. So on phase A, we'll ramp the power down to 70% or up to 130%, or in those steps in between. And we will also, when we do that, tell the model that's in an unbalanced mode. And we had trouble just from the terminal quantities to know if the model was unbalanced. You have zero sequence voltage that could be detected, but it's not a very robust method. So we're going to leave that for later. Maybe a negative sequence relay or some other protection function would know if the model is going to be in unbalanced mode. Moving on to the next slide. So these are the original time varying D and Q axis components, and we have the voltage, VD, VQ, V0, and ID, IQ, and I0 across the top. And so for the first half of each transient, you can see they are flattening out to steady levels, DC levels, but when the single phase load disturbance initiates at 3 seconds, you get oscillatory behavior. And it's either, again, 60 hertz or 120 hertz. So what we do is we filter it into low pass and high pass components. Details shown below there, but basically that's going to break those oscillating components down into steady quantities that we can train to. So we have, apart from say some transient impacts on V0 and I0, at the time of the initiation of the transient, there's some small values, some non-zero values there, but basically they begin and end at 0. And the DC high pass and low pass quantities is something we can fit in the training process. So next slide, please. Okay, these are the quasi-steady outputs that we're trying to train against, same as I showed in the previous slide. But these are what the HWPV model is trying to fit, and you can see those are steady DC quantities, except for some small low-level transients there. Next slide, please. So in terms of implementation, I mentioned earlier that we're fitting in the Z domain, and for time domain like EMT simulator, we want to re-implement that in the S domain. Basically, we're using the forward Euler transformation to do that, using the Herald toolbox in Python, and it's giving stable results for the models we fitted so far. We've implemented in Helix, which is a co-simulation framework, so we have a Python implementation that talks to other federates. UCF has implemented the HWPV for simulation in MATLAB, and then PNL has done it in ATP. We started to look at PSCAD, but we think for that and other tools, we're probably just going to stick with Python in this project and federate them over Helix. You can do a faster, better job with tool-specific user code or C or Fortran, and it's going to run faster, but it's not portable. But speaking of portability, the model coefficients are just in JSON files, so they are bias and weighting coefficients for the neural networks, and then numerator and denominator coefficients for H of Z or H of S. So pretty simple to transfer the models back and forth. Next slide, please. So I think this is close to my last one. This is an ATP simulation result, so it runs in about a second using the transient analysis of control systems feature. Anybody else happens to be using ATP, feel free to email me. But basically, in the interest of time, feel free to ask a question about it, but zoomed in on the on 9 seconds, there's a single phase load transient indicator. You can see the voltage drops on phase A. The currents on phase A, B, and C increase slightly. And then you can see in the lower right, the D and Q and 0 axis voltages have oscillatory components, either at 60 hertz or 120 hertz. Okay, next slide.
Thank you, Tom. So based upon the average model or HW model, then we can proceed with the GFM and GFL control design. The approach we're taking is to design control using state space model. In other words, it's a model-based analytical design that utilize the dynamic equations of both the inverter as well as the components, the circuit components within. And the control framework has several parts to it. The goal here is to control the whole vector of voltage, current, active, reactive power, frequency, angle, and current. So the way we design the control is we have several modules. Start off from the left, we have input constraint enforcement, looking at all the reference input as well as the measurement on the quantities, physical variables, and make sure they are within the range. And that includes for PV inverters, the instantaneous power that is available from the DC stage. Based upon the reference inputs and the dynamic model, we design nominal tracking controls. And it does have a current loop and have another loop that is either voltage or power, depending upon GFM or GFL. And these nonlinear feedback controls would be able to guarantee the nominal operation of tracking performance. Then we have a block that enforces state constraint, constraints on the state variables. These enforcement control is to ensure that while we control some of these variables in terms of tracking performance, we don't violate other constraints that the system is subjected to. And these controls then gets applied to the physical system, which has the switching and the EMT dynamics involved, and then we take the feedback. So it is a pretty standard state space design. What we're trying to do is to basically, make sure that all nonlinear relationships are taken into account in the control design so that we have better performance and we enforcing all the constraints. So we're going to show some of the very basic aspect of the control design, and we start with the LCL filter that typically follows with a switching transistor-based inverter. And these filters obviously are well understood, and at standard operating frequency, the dynamic equations are shown on the graph on this slide, and it's a 9th order differential equation, and we can then map into the DQ0 frame. What's not shown here is the switching dynamics. There, we either have the average model, which assumes the voltage right after the switch is proportional to the DC voltage, or the HW model. Any model, any other type of EMT model, due to the lack of analytical representation, it's very hard to be used for real-time control. And that's why part of the reason we're also doing the HW model. And more on that later. So for our control design, we consider the general case where the system can operate either in a balanced or unbalanced mode. In either case, for a arbitrary three-phase waveforms that is not balanced in either the angle or amplitude, it is straightforward to show that its DQ0 component consists of steady state, constant term, theta 0, and oscillatory terms, theta 1, eta 1, eta 2, associated with the basic frequency. And then you have eta 3, eta 4 that are associated with 2 times omega. And these quantities can be calculated in real time. And the goal here is to, depending upon the control objective, to suppress the oscillatory part of the DQ0 component. What's shown here on this page is the voltage expression. The current expression is analogous, so that you have also 6 quantities, either V1 to V6 or I1 to I6 that represents the amplitude of these various components. Based upon these components, then we can calculate instantaneous power, P of T, average power, capital P, as well as oscillatory power, O1 and O2. These quantities come straight from the expression of instantaneous power. We also can compute based upon the extension of single-phase reactive power expression to 3-phase. We can calculate what the reactive power is. And for unbalanced operation, the reactive power is generally different from the oscillatory power. And so in the control design of unbalanced 3-phase operations, we can actually control all these quantities, and the details will be shown later. So in terms of the grade forming control, it consists of 2 tracking controllers. The first one on the first line, showing in terms of equation, is the frequency and angle tracking control. And it's very straightforward to show that based upon an integrator, that the frequency and angle can track their references. The nonlinear coupling is through the frequency into the voltage and current equations, and the corresponding tracking control are shown on the second and third line on this slide. And for unbalanced operation, the feedback signals, such as the output voltage in DQ0 frame, they are oscillatory, which means that the current reference, the voltage tracking control, would be time varying controls. And some of the calculations are shown in terms of their rate of change, are shown on the bottom of the page. So they are corresponding to the frequency, as well as the 2 times the frequency. You have these components. And these model-based tracking control enable us to track both balanced or balanced quantities, whether it's voltage or current. Obviously, for practical applications, we like to achieve as balanced tracking performance as possible, at the same time minimizing reactive power as well as oscillatory power. For grade following control, the inner loop voltage tracking, the current tracking is very similar. What's different is the outer loop tracking control, where we can specify in terms of a control objective, active power, oscillatory power components, O1 and O2, as well as the reactive power. Based upon those references values, we can pick the current reference, which is shown in the middle of the right column. Once the current reference is calculated or is formulated, then the current tracking would allow us to inject the powers that that the GFL control is aimed to do. And these analytical expressions can be easily programmed in Simulink, and they can be computed real time. As we mentioned earlier, one of the key aspect of the state space design is that it provides better performance, including enforcement of any constraints. We'll show constraint in a minute. The basic idea of constraint and control design is shown on this particular slide. If you will consider a first order system and you want the output be within plus minus sigma band around a equilibrium point, then the control to achieve this is actually within certain range. So you will have a band or region in the control subspace where you can choose your control to ensure the satisfaction of those constraints real time. And what this allows us to do is to balance various requirements. While we're trying to control the active and reactive power, we need also looking at, for example, how voltage and current is going to change. And conversely, when we control the voltage, we need to look at how current is going to change. And this allows us to basically optimize against a set of objectives, not just one, not a single control design. So this basic concept can be easily extended to high order systems by using the outproof approach and also differential inequalities. By applying backstepping, you will be able to design control and determine the admissible control set within which the control can be chosen without violating the constraints, which in turn allow us to design either GFM or GFL controls with all the constraints satisfied. The constraints we consider in the control design are shown on this on the top portion of the slide, which includes the frequency, the output voltage, the Q component of the output voltage, PQ, as well as the capacity S, and the current. For each and every of these constraints, one can go through the derivations illustrated on the previous slide so that you will get a region for the control. And if you would consider, for example, voltage and PQ as well as the Q component of voltage, you'll get a set of inequalities. And what we can do then is to design a tracking control and then project that control onto the set where you were able to then satisfy the constraints. At the same time, try to accomplish the control objective as best it can. So all these expressions are analytically derived, and again, they're straightforward to implement in Simulink. So in summary, the proposed control uses the state space model to explicitly consider all the state variables in terms of a control design, as well as the constraint enforcement. The end result is that whether it's GFM or GFL, they have the same components. Specifically, you will have the same current control loop and frequency control, with the exception that the frequency control for GFL does not involve angle. And the out loop tracking control would be either power tracking or voltage tracking. And the structure of the control remain the same. The only thing different is the control objective, and the enforcement of the constraints also remain the same across both of the control types. So what I'm going to show is a couple cases where you can kind of get an idea of what type of performance these state space control can provide. What's shown as a case 1 is a 4-digit microgrid whose topology is showing on the upper right corner. Between 0 to 20 seconds, 4 DGs, black start asynchronously. DG1, which starts first, stays as a GFM. One of the DG goes from GFM to GFL. The other 2 DGs stays at GFL. And during the process of asynchronous start, once the grid is formed, there's a secondary control can kick in, which enables load sharing. So you will see on the upper left plot that around 15 seconds or so, once all the DGs get started, there is a consensus in terms of output power. And at the t equal to 20 seconds, grid forming inverter DG1 is intentionally turned off, or is subject to attack that was disabled. Then in that case, among the remaining DGs, the one with, let's say, the maximum capacity, of course, different schemes can be implemented. But what we did is implement the scheme where the maximum capacity DG will act as the grid forming. And in that case, the DG2 kicks in and maintains the voltage after a very small transient. And then the rest of the DGs would either work as a GFM or GFL, depending upon their priority. And as you can see here, the GFM provide the rapid response, whereas the GFL would able to do the load sharing with both GFL as well as GFM. In case 2, showing on the left, we tested communication disruptions. Here we have grid forming and secondary control gets activated automatically. And when the communication through the secondary control gets disrupted, the only thing happens is that the load sharing capabilities through the secondary control will be disabled. And you will see that the injection of power will diverge. But once the communication comes back, they will converge again. The reactive power is not set to be doing load sharing. That's because we wanted the voltage to be at 1. If we allow small variations around the unity voltage, then we can also achieve a reactive power consensus. Case 3 on the right, showing what would happen when changes happen in the PV inverters. In particular, in this case, both DG1 and DG3, their maximum capacity, they're represented by blue and the yellow color, goes down rapidly, or slowly in this particular case. Then obviously their output would have to be brought down, and then the GFM would basically provide both active as well as voltage support when it changes. Because we have constrained enforcing control, whether changes happen voluntarily or involuntarily, these constraints, they are automatically gets enforced. Case 4 shows what happens when we have asynchronous start, and then after that, we have faults, whether it's single line to ground or 3 line to ground or induction motor start. What they're showing here is that what the plot's showing is that with constrained control, you can impose not only the maximum output power each of the DGs can provide, dynamically, but also as the fault occurs, the current would be limited, and that provides much better ride-through capabilities for the inverters, which ensures the appropriate operation based upon the IEEE standards. The last case we want to show is the capability of GFM and GFL controls in their regulation of unbalanced voltage and the current. What we're showing here is that before t equal to 2 seconds, the system is operating in a balanced condition. After t equal to 2 seconds, the system becomes unbalanced. As you can see, the instantaneous power of the GFM becomes oscillatory, while the GFL, because of its power injection control, it remains to be tracking the reference. Now, what happens is that for both GFM and GFL, we can control the active power and the reactive power injection, as well as oscillatory power. And for GFL, you can also see for different phases, the voltages are not balanced because they are not regulating voltages, whereas the GFM, their terminal voltages are regulated to be balanced. So our control basically allows us to use the dynamic model of the system to ensure GFM and GFL performances. So therefore, it's critical for us to get a good model, and the Hammerstein-Wiener model is the one that we're moving toward to. And what's showing here on the screen is the data that we collected using both the Simulink model of the grid link inverter, as well as in the near future, the physical grid link inverter itself in terms of the HW modeling. Now, one of the technical issue we have to solve in terms of using model-based approach is that we have to know the model. So the question we need to answer is, in case that you have a black box where the existing, say, a certain vendor provides a grid forming or grid following inverter, how do we get the model and implement it? One of the things that we can do is, even though we may or may not have the native LCL filter, we can design using observer-based control methodology, design an inverse LCL filter or inverse LC filter for the control design. And the control would act upon that particular filter. And what we like to show here is that there is a systematic way of going about doing that. Is that you find the inverse mapping, which is showing on the bottom left of this slide. And this inverse mapping would allow us to basically estimate what would be the voltages, RMS equivalent voltages after the switch, given the nominal values. They don't have to be accurate, is the value that we want. And then the control can be designed based upon those nominal values. Because this is this mapping is invertible. For example, here it shows the comparison of the VS estimate in terms of ABC versus the actual switching circuit output, and you can see they are different, but nonetheless, in terms of RMS equivalents, they are equivalent, and this is checked by comparing the output under the control that under the UDQ U0 that is designed based upon the LCL filter that we selected in the control design. So as you can see, the actual circuit output versus the estimated output, they are overlapping. very accurately, which means that it provides us a mean of implementing state space model, even if we don't have access to the internal mechanism of the inverters itself. So that brings us to the point where we can then integrate the HW model and the existing switching circuit into the control design and compare it against the average model that we typically use in the control design. So this is the block diagram where we would have the circuit with inverters, which is on the top row. And then in the middle is typically what we do in the control design using average model. And then the bottom row is the HW model that provides the input-output relationship. We tested a number of, UDUQ. These are for balanced operation. And what you see is that under these choices of open loop controls, sometimes the HW model performs better than the average model. Sometimes average model performs better than the HW model. And the reason is because it is actually this advantageous for the average model to perform better, because in the circuit, we're using the real DC currents and DC voltages to drive this average model, which in the actual implementation of a purchase inverter, that may or may not be the case. Some of the even the software-defined inverters does not provide a DC measurement. We're in the process of implementing the grade forming control using the HW model and compared versus the average model. This is the same diagram that we used for the open loop. We're working on in the closed loop setting. And the current result is showing here on this slide between 0.1, between 0 and 1.1 second. It's an open loop control. We let the capacitor to charge. We let the system to settle down. And then at t equal to 1.1 seconds, the GFM control kicks in. What you see here is that the average model actually matches with the real circuit quite well. The HW model is showing certain errors, and the reason is that when we deal with PV inverters, we actually had to put additional control into the DC stage so that the DC voltage, which is showing on the right, is maintained to be constant. W model was based upon open loop data. We didn't train it using the DC voltage controller that we have currently designed. So that's why we have the discrepancy, and we hope to go back and redo this process and get a better HW model so that we can integrate into the real-time control scheme. The goal for us would be redesign the control to compensate or attenuate the EMT, and the way to do that is actually to incorporate the HW model, compare its performance with the average model which we design our control with, and develop this adaptive control components that would dynamically compensate for the EMT in real time. That is the step we're currently working on, and we hope to share results with you in the near future. Thank you.
Okay, great. Fantastic presentation.